This next video is on solving IVPs using Laplace transforms, solving differential equations with boundary conditions. Here's a differential equation. d squared y dt squared plus 8 dy dt plus 15y equals 0. You can also rewrite it as using the y double prime plus 8y prime plus 15y equals 0. And the boundary conditions that are given, initial conditions, are y of 0 is 1, y prime of 0 is minus 2. It doesn't matter which notation you use, so they can give you the differential equation either way. What we need to do, we need to transform the entire equation. So transform this whole thing. Y double prime plus 8y prime plus 15y equals transform of 0. Alright. The right side doesn't have to be 0. The good thing about using Laplace transforms is you can solve non-homogeneous equations the same way. So for example, if we had something on the right side like sine 3t, you just transform sine 3t. And the transform of sine 3t is 3 over s squared plus 9. It does not make it more difficult. If you have t squared on the right side, you can also transform t squared. You can have anything. Cosine, if you have e to the 3t, its transform is 1 over s minus 3. So you just transform it. The transform of 0 is 0. And I'm going to separate these terms now. So the transform of y double prime plus 8 times the transform of y prime plus 15 times transform of y equals transform of 0, which is the integral of 0, and it's a definite integral, so it's 0. I was able to do this because the transform is an integral, so I can take those numbers out. Alright, let's put this in a pair of red brackets, and I'll put this transform here in a pair of blue brackets. So we need the transform of y prime and also the transform of y double prime. The transform of y prime is equal to s times transform of y minus y of 0. And the transform of y double prime is s squared transform of y minus s y of 0 minus y prime of 0. We proved these before. So this would be the blue bracket. This would be the red bracket. What we're going to do next is replace transform of y double prime by what's in the red brackets. Transform of y prime by what's in the blue brackets. I'm going to do the algebra. So here's the equation. Transform of y double prime plus 8 transform of y prime plus 15 transform of y equals 0. Okay. Transform of y double prime is the red bracket, so I'm going to replace it by this. S squared transform of y minus sy of 0 minus y prime of 0 plus 8 transform of the derivative, which is s transform of y minus y of 0 plus 15 transform of y equals 0. Alright, we have y of 0 and y prime of 0. Y of 0 is 1 and y prime of 0 is minus 2. So I'm going to replace this by 1 and this by minus 2. So I'll end up with this s squared minus s times 1 minus y prime of 0, which is minus 2. I'm going to remove the red brackets now. We don't need them anymore. Plus 8s transform of y minus 8 times y of 0. Y of 0 is 1, so it's minus 8 times 1 plus 15 transform of y equals 0. Okay. Our unknown is transform of y. So I'm going to factor that out. Transform of y times s squared plus 8s plus 15. Okay, I've used this term, this one, and this one. All right, minus s plus 2 minus 8 equals 0. All right, so transform of y I don't need a bracket now, times s squared plus 8s plus 15. Okay, this is minus s plus 2 minus 8, which is minus 6. Minus s minus 6. Okay, take it to the right side and it becomes s plus 6. Therefore, transform of y equals s plus 6 over s squared plus 8s plus 15. Next, we need to invert this, and once we invert it, that will give us the solution of the original equation. So y is the inverse of this. Try to factor the denominator and use partial fractions, okay? S plus 6 over s squared plus 8s plus 15 equals, okay, this is s plus 6 over s plus 3 times s plus 5. So we need to break this fraction up into partial fractions over s plus 3 and s plus 5. We need to figure out what goes on top. This is linear, so what goes on top is a number here, a, and a number here, b. And now we need to do partial fractions. So s plus 6 over s squared plus 8s plus 15 equals, rebuild this, so it'll be a s plus 5 plus b s plus 3 over the products of those two denominators. Okay, these two sides must equal each other, so s plus 6 must equal the numerator on the right side. And that's going to give us two linear equations to solve for a and b. It's going to look like this. S plus 6 equals a s plus 5 plus b s plus 3. I'm going to use method 2 to solve this. Take two numbers for s. Okay, I'm going to take s equals minus 3. S can be anything. So minus 3 plus 6 equals a times minus 3 plus 5. And the reason why I took minus 3 is because minus 3 plus 3 is 0. So that gets rid of the second term. Then I'm going to take s equals minus 5 in a minute. So this is 3 equals 2a. Therefore, a equals 3 halves. Take s equals minus 5. So that will give us minus 5 plus 6 equals 0. Minus 5 plus 5, that's 0. Plus b times negative 5 plus 3. 1 equals minus 2b. So b equals minus a half. Put these back in the partial fractions right here. So what we're trying to invert is this. Inverse, here's what we had. A over s plus 3 plus b over s plus 5. So it'll be s plus 3, s plus 5. Okay. Up here we have a, which is 3 halves. We got that. And then b is minus a half. So you can put plus minus a half or minus a half, like this. When you're inverting this, this will be 3 halves. The inverse of 1 over s plus 3 is e to the minus 3t minus a half e to the minus 5t. And this was y. This is the solution of the original IVP. We don't have to actually solve the equation and then find the constants. It could have been non-homogeneous, homogeneous, anything. This is the final solution, including the constant C1 and C2. So that's what's good about this method.